Hey everyone, welcome back. In this video, we're going to finish up Chapter 9, Section 3 by looking at powers and roots of complex numbers. Okay, so to start off, we're going to look at powers of complex numbers, and we're going to look at this using what we've learned about products of complex numbers. So we talked about multiplication and division of complex numbers earlier in the section using their polar form. Here we are going to use those concepts, specifically the product concept, to see what pattern emerges when we look at the powers of complex numbers. Okay, so what we're going to do is we're going to start off with z equal to just the general form, polar form of a complex number, r times cosine theta plus I sine theta. If we look at z squared, so squaring z, raising it to the second power, that's equal to z times z, which, if we use what we know about products, gives us a magnitude of r times r, or r squared, and an angle of theta plus theta. We add up the angles. In other words, 2 theta. So r squared times cosine 2 theta plus I sine 2 theta. If we raise z to the third power, that's the same as z squared times z. So again, we take the two magnitudes and multiply them. We have r squared times r, which gives us r cubed. We have 2 theta plus theta, which gives us 3 theta. Okay, so here you can start to see a pattern emerge. Whatever power we're raising z to, we're raising the complex number to, we're taking the magnitude and raising it to that power. And the new angle is going to be the original angle multiplied by n, multiplied by the power. Here we have 3, r to the third power. Our new angle is 3 theta. Okay, this is what we call DeMoivre's theorem. So it just has a fancy name for this pattern that we see emerging. So generally, if we have a complex number written in this form with a magnitude of r and an angle of theta, then z raised to the n power is going to be equal to r to the n power times cosine of n theta plus I sine n theta. So pretty straightforward. We raise r to the nth power and multiply theta by n, whatever power we're raising z to. Okay, so here we're looking at roots of complex numbers. Here we're going to use the general form. We're just going to let w equal, so instead of z, we're talking about w. Let w equal r cosine theta plus I sine theta. There are n distinct complex roots of w. So n could be 2. You could be talking about square roots. N could be 3 cube roots. When you talk about cube roots, for example, you're going to have 3, and distinct means separate, 3 separate roots. So they're going to be different numbers of w, and they can be found using the following formula. So this formula is a little similar to DeMoivre's theorem. We have d sub k, so we'll come back to the k in a second, is equal to the nth root of r times cosine of theta divided by n. So instead of raising r to the nth power, we're taking the nth root. Instead of multiplying theta by n, we're dividing theta by n in this case. Plus I sine theta divided by n. Okay, so this part is similar to DeMoivre's theorem. We're just doing the opposite, taking the root and we're dividing. There's one extra part that we're adding on, which is 2 k pi over n. Or I'll usually write it as just 2 pi times k over n plus 2 pi times k over n. And the 2 pi there is just, if we're using radians, it's going to be 1 revolution. If we use degrees, it's going to be 360 degrees instead of 2 pi. And this is connected to k, so notice we have z sub k. All of the roots are given by this formula, where k starts at 0 and ends 1 less than n. So 0, 1, 2, and so on until we get to n minus 1. And that gives us n number of roots. For example, if we're looking at square roots, we start at 0, we go to 1, and then 1 is less than 2. 1 is 1 less than 2 specifically, so we have 2 square roots. If we have cube roots, we have 0, 1, 2. We end up with 3 cube roots for a number. So we're going to go through all of these, write them out one by one for each k, and then simplify from there. Let's go over a quick example. What I want to look at is finding the cube roots of I. So here we just have I. In this case, I is equal to, if we wanted to write this out in polar form, going to be equal to 1 times cosine of, let's use degrees, 90 degrees, plus I sine of 90 degrees. Okay. So I rewrote I in terms of polar form, and then we're going to use the equation above to find the 3 cube roots of I. We're going to start off with k equal to 0. So we set k equal to 0, and then we calculate this part of the equation when k is 0. So our first root, z sub 0, is equal to the nth root of r, so the cube root of 1. And the magnitude is going to be the same for all of the roots. We're always going to start off with that nth root of r. That doesn't change depending on k. Cube root of 1 times cosine of theta is 90 degrees divided by 3 plus, instead of 2 pi, we're going to do 360 degrees because we're talking about degrees, times k, which in this case is 0, divided by n, which is 3. Plus I sine, and we have the exact same angle, 90 degrees divided by 3, plus 360 degrees times 0 divided by 3. Okay, so here you can see the second part, this part is just going to be equal to 0 because k is 0. So when we simplify, we end up with a magnitude of 1 and an angle of 30 degrees. Okay, so that's one of our cube roots. Let's take a look at another cube root. Here we set k equal to 1, increase by 1, and then we'll fill out the right side with k equal to 1. So we have z sub 1, same magnitude, cube root of 1, times cosine of 90 degrees divided by 3 is just going to be 30 degrees. So we can simplify that right away. Plus 360 degrees times 1 divided by 3. Plus I sine of 30 degrees, same exact angle, 60 degrees, 1 divided by 3. Okay, so here z sub 1 is equal to just 1 for magnitude, cosine times cosine of 360 divided by 3 gives us 120 degrees. If we add 30, we have 150 degrees. Plus I sine 150 degrees. Okay, so that's our second cube root. Our third cube root and last cube root is going to be when k is equal to 2. We'll just end up with 1 in front, because it's cube root of 1, times cosine of, we start off again with 30 degrees, 90 divided by 3, plus 360 degrees times 2 divided by 3, plus I sine, and that exact same angle, 30 degrees plus 360 degrees times 2 divided by 3. Okay, so z sub 2 is going to be equal to 1 times cosine of, and in this case, we have 120 times 2, which gives us 240, plus 30 gives us 270 degrees, plus I sine 270 degrees. Okay, so the 3 cube roots of I are going to be z0, z1, and z2. In other words, complex numbers, all of them have a magnitude of 1, and then the 3 angles we're looking at are 30 degrees, 150 degrees, and 270 degrees. So this is how we can write out the n roots of a complex number, in this case, the cube roots of a complex number, starting with k equals 0, and then we go down the list. To show why this is true, we can look at the complex plane and think about it graphically to help us out. Okay, so here, a rough sketch of the complex plane, imaginary plane, real plane, or sorry, imaginary axis, real axis. And we know that we're going to end up with I as our final number. One of the numbers, as we saw, was 1, at a magnitude of 1, and an angle of 30 degrees. So we're at about 1 and an angle of 30 degrees. And I'm going to use a color for this, angle of 30. So here theta is just 30 degrees, and r equals 1. When we raise this number to the third power, in other words, it's a cube root of I, what we're doing with the angles is we're multiplying the angles by 3. We're adding 30 degrees 3 times. So we start off with 30 degrees, we add another 30 degrees, and we add another 30 degrees to end up at 90 degrees, which is the angle for I. Another cube root, so this makes sense, we're just adding 33 times. Another cube root is, stop here, 150 degrees. So still 1, but 150 degrees. Here, when we multiply this number by 3, or sorry, when we raise it to the third power, equal to 1, theta equals 150, we add 150 degrees 3 times. So 150 plus 150 gives us 300, plus another 150 gives us 90 degrees. So here, when we add 150 3 times, or multiply it by 3, because of the cyclical nature of the complex plane, we end up back up at 90 degrees. The same exact thing happens if we look at our last complex number 2. 270 degrees. R equals 1, theta equals 270. And 270 degrees, you can see, is 90 degrees times 3. So 270 degrees. In other words, we go 90 degrees 3 times. We're going to add another 270, so we're going to go 90 degrees 3 more times to get here. And then we'll add another 270 to end up at exactly 90 degrees. So the reason why we have these different complex roots is because if we look at the angles, they're going to loop back around and end up at the kind of like goal angle. So all 3 of these, when we multiply the angle by 3, we end up at 90 degrees.